Hello, and a warm welcome to all the audience of this course. Today we are going to start a new topic, which is known as influence line diagrams. Okay, so why do we need influence line diagrams? What influence line diagrams are, and how to draw influence line diagrams? All these things we are going to discuss today. Okay, so today is an introductory class of the topic of influence line diagrams. So actually, till now in the subjects of mechanics of solids as well as structural analysis. Um, Till now, what we have mainly discussed is the dead load or the dead loads, okay, and how to draw the shear force diagram or bending moment diagrams of the dead loads, okay. Till now, our focus has been on the dead loads. Therefore, in the mechanics of solids subject, you were given a certain dead loading and you used to make the the shear force diagram and bending moment diagram. So those were the static loadings. Static loading means the loadings which are not moving. Okay. So that was the case, and that case was addressed by drawing the shear force diagram and bending moment diagram. So what information does the shear force diagram or bending moment diagram provide to us? The information which they provide is at every point of the beam. So below the beam, we make the shear force diagram. Below the beam, we make the bending moment diagram. For example, if you see here, you are having you are having a certain beam, and it is having some loading above it. Let's say UDL is there, or there is a point load, or there is a concentrated moment also, right? So different kinds of point load, P1, P2, M, W, whatever it may be, but the loading was always static. That means the loading did not change with time. And you used to draw the shear force diagram of this blah blah blah, some sort of diagram, and bending moment diagram you used to draw. Something, 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 some diagram will be there. So that means at this point in the beam, this is my shear force. At this point in the beam, this is my shear force. At this point in the beam, this is my shear force. At this point in the beam, this is my shear force. Okay. Similarly, at this point in the beam, this is my bending moment. At this point in the beam, this is my bending moment. At this point in the beam, this is my bending moment. At this point in the beam, this is my bending moment. So that's how the shear force diagram and bending moment diagram used to give us the uh, distribution of shear force or bending moment across the span of the beam. But now the problem is we are talking about moving loads. Okay, moving load means the loads which are not static, which are moving across the beam. Okay, for example, let's say there is a car which is coming and it will step over the beam. After some time, the car will be here. After some time, the car will be here. And after some time, the car will pass away from the bridge. So, influence line diagram helps us to find out at a particular section how the shear force is going to vary when the vehicle passes from x is equal to 0 to x is equal to n. Similarly, it tells us how the bending moment varies at any given section of the beam as the loading moves from x is equal to 0 to x is equal to n. Similarly, how the support reactions, this might be your end A, this might be your end B. So how your support reactions are varying with the passage of the load. Okay. So the beauty of this method is that there could be infinite kinds of loads in the world which are possible, which may pass through a beam or a bridge girder. You don't have to draw separate diagrams to find out the variation of shear force at a point. We draw influence line diagram for a unit load and we simply multiply the ordinates of the graph with any arbitrary loading which might be given to us. Okay, so What are influence line diagrams? Influence line diagram influence line diagrams influence line diagrams represent variation of variation of any stress function any stress function, namely support reaction and shear force and bending moment. Okay, so these are the things which are going to find. So when the load from one end to the other, from one end to the other. Okay, so this is relevant for it is relevant for roads, bridges, and so on. Okay, so now we are going to learn how to draw influence line diagrams. Method to make influence line diagram. Okay, so how do we make it? That we are going to see now. So firstly, we'll consider a case where simply supported beam is there. Okay, for simply supported beam, we are going to make the influence line diagram. So how do we make it? First of all, let us draw a simply supported beam. And we take a unit load. Okay, this magnitude is 1 and this distance is x. Okay, so for this positioning, we are going to find out the distribution of support reaction. Okay, so there will be a vertical reaction here VA, there will be a horizontal reaction HA, vertical reaction here at VB. Okay, so drawing diagram for support reaction at A. So this is RA or specifically VA. Okay, so to do that, it is very easy. You have to simply do the moment equilibrium about B point. Summation NB equal to 0 implies VA into L is equal to 1 into L minus X, where L is the total length of the beam. So if you solve this, you will get VA is equal to L minus X by L. You should remember this. Okay. At X equal to 0, my VA value is 1. At X equal to L, my VA value is 0. Okay. So if you plot this graph, how it will look like? There will be a straight line. This is your x equal to 0 and this is your x equal to L. So at x is equal to 0, VA value is 1 and x equal to L, the VA value is 0. So join it with a straight line. This is your influence line diagram for VA. Okay. Similarly, if you want to find out how the support reaction varies at joint B, so you can do it like this. For that you do summation MA equal to 0 and that will give you VB into L is equal to 1 into X. So my VB equal to X by L. Okay. So once we've got this expression at X equal to 0, my VB value will be 0. At X equal to L, my VB value will be 1. So now you can plot this graph. Your baseline. This is your 1. Oh, sorry. X equal to 0, VB equal to 0. At X equal to L, VB equal to 1. For VB. Okay. So this is how we can draw the ILD for X equal to 0 and X equal to L value we can plot and we can combine them to get this graph. So what this graph tells you? This graph tells you the variation of support reaction when one unit load moves on it from X equal to 0 to X equal to L. Okay. So now let us make influence line diagram for shear force. If you are drawn with all this, so I'm gonna rub all this. Now, if you want to draw ILD for shear force, third case, ILD for shear force at a given section. For that, again draw the beam and put a unit load and tell the section where we want to find the shear force variation. Okay. Let the total length of the beam be L and the distance C or the distance of point C could be A. Okay. And this is X. Okay. So now if you want to find out shear force at section C, so you are interested in only the section C, right? And you want to know the variation of Want to know the variation of shear force at C as the load passes from x equal to 0 to x is equal to L. Okay, so it is very simple. There are two cases. Two cases arise. First, when moving load is before C, because C is the section of interest. And second, when moving load has passed C point. Okay, so solving for the first case, the case is as follows. This is my point C, this is my 1, this is my X. So this is my Bn, this is my Am. Reactions we already calculated. This is x by L and this is 1 minus x by L. So if I cut the section at C, this is my Vc, this is my 1 minus x by L, and this is at x distance, there is 1 unit load. So if you solve for this, you will write Vc plus 1 equal to 1 minus x by L. So Vc comes out to be minus x by L, or I can also call it Vc equal to minus of Rb. Okay, check that Rb equal to x by L. Okay, so shear force varies like this when it is before, I mean the load is before point C. So let me shift this part a little bit on this side because my photo is obstructing your view of the nodes. This is what we are saying. Now solving for the second case. Second case, this remains the same support reaction. The section C also remains same. But 1 unit load is no more here because it has passed through section C. And so your equation becomes Vc equal to 1 minus x by L, which is also equal to Ra. Okay, now we can plot the graph. If I make this entire thing a bit smaller, okay, so now we can make the graph of this. So this is my baseline. Section C down. Now at x, from x equal to 0 till x equal to a, when here I can write this is x lies from 0 to a and x is greater than a and less than l. Okay, so for this case if I draw, it is 1 minus x by l. Okay, so at Vc equal to 1 minus x by L. So at x equal to 0, VC value is so when, sorry, this I wrongly wrote. X lies from 0 to A, and x lies from A to L. When x lies from 0 to A, the graph is minus x by L. So x equal to 0, the value is 0, and x is equal to A, the value is minus A by L. Minus A by L, right? And if I see the graph after A, so at x equal to A, as soon as the point moves, the moving load moves slightly beyond A, its value becomes 1 minus A by L. So that means it will have a jump of 1 unit. And the value will be 1 minus A by L. Or I can write it like L minus A by L. And then the value finally becomes 0 at x equal to L. Okay, VC equal to 1 minus L by L. So this is our graph of ILD for shear force. Shape of the graph is always going to remain like this. Okay. So now coming to the next part, which is ILD for bending moment. Okay. Its coordinates we can remember that it is minus A by L, and this is L minus A by L. L minus A by L. Now we are going to draw ILD for bending moment. I have again two cases. Here is my beam, and there is a second support, and this is a section C where I want to know the variation of bending moment as the moving load moves from end A to end B. So this is your 1 unit load, this is the distance x, right? So now you can take two cases. Case 1, when x is from 0 to A, same are there, this is A and this is L. So when x lies from 0 to A, if I separate the section, so support reaction I already calculated, this is x by L, this is 1 minus x by L. Okay, so if I cut a section here at C, this is 1, this is x, this is 1 minus x by L, and this distance is A minus x. So bending moment at C, sagging bending moment we take by default positive. So M equal to 1 minus x by L multiplied by A minus 1 into A minus x. If you solve this, you will get A minus Ax by L minus A plus x. If you solve this, you will get x into 1 minus A by L. And for the second case, case 2, when x lies from A to L, at that time, this 1 unit load is not going to come into the picture. So let me reduce the scale of this writing. is case 2. Solving. For case 2, again, you draw the section. Bending moment is M. This is 1 minus x by L located at a distance A. So M equal to 1 minus x by L multiplied by A. Why? Because the unit load has already passed it. Now we can draw the graph of this one. Draw the graph. To draw the graph, we can see when x value is 0, the value is 0. When x equal to A, the value is A into 1 minus A by L. Now as soon as the point moves beyond C, the point load moves beyond C, the value becomes A 1 minus A by L. So from case 2 equation also we are getting the same point as A 1 minus A by L if you put x equal to A here. And same A into 1 minus A by L if you put x equal to A here. Okay. And then finally at x equal to L the value becomes A into 1 minus L by L, which is 0. So the graph will meet here as a straight line. So the ordinate value here is A1 minus A by L, or you can also write it as, by taking LCM, is A L minus A by L, or you can also write it as AB by L, where B is the remaining length. Okay, the entire graph is positive. So this is the graph. Okay, AB by L. So always remember the ordinate point as AB by L equal to 0. This is ILD for bending moment. So few points to see here, that the graph of influence line diagram for bending moment is always positive. Okay, it's always positive. So bending moment increases and then decreases, but the value always remains positive. That means sagging bending moment. Okay, for the moving load case. But when you go for the shear force diagram at the section is partly shear, it's not the shear force diagram, it's the ILD for shear force. You can see the graph is having a jump at x equal to A. This is x equal to 0, this is x equal to L, this is x equal to A. Okay, so this is x equal to N. So here there is a jump. So this will create slight issues when we are solving numericals. Always remember that at shear force, shear force ILD has a jump at x equal to A, and this you should always keep in mind. And also you can see that if you extend this graph in this direction, this is nothing but when x is equal to, this is minus RB graph. Okay, and if you extend this graph up, it is RA graph. So its value would be 1 here, its value would be 1 here, minus 1 here. Okay, always remember this. And if you talk about the ILD for RA and RB, I have rubbed those figures. Those are the simple ones, very easy. That the graph is 1 here, 0 here, at x is equal to 0 and x equal to L. This is your RA, and similarly this is your RB. So in today's class, we learned that what is influence line diagram. These diagrams are very important to know the variation of shear force or bending moment at a particular point in the beam, at a particular section in the beam. And we also learned how to draw these diagrams for the case of support reaction, RA and RB, and shear force and bending moment. So in the next class, we are going to see few numericals based on these concepts. Thank you very much. I hope you liked the class.